Have you ever found yourself just staring into your fridge, wondering how on earth it actually works? What's the magic that keeps your milk from spoiling? We kind of think of it as just a box that makes things cold. But the real story, oh, it's so much cooler than that. Let's get into it.
So yeah, how does it really work? Because it's not just a box. It's a brilliant piece of everyday engineering. And inside that quiet, humming machine, there's this incredible, hidden journey happening over and over and over again, 24/7.
Okay, so here is the absolute key to understanding everything. Your refrigerator doesn't create cold. That's not a thing. What it is a heat mover, a heat pump. Its entire job is to grab the warmth from inside your fridge and dump it out into your kitchen. We're going to follow that heat on its wild ride.
To really get our heads around this, we're going to start with the storybook version first, the perfect textbook refrigeration cycle. This is what it would look like in a flawless world, with zero friction and absolutely no wasted energy.
And the hero of our story? It's this special fluid called a refrigerant. Seriously, think of it like a tiny sponge for heat, just cycling endlessly through your fridge's veins to soak up warmth and carry it far, far away. So our little hero's mission kicks off deep inside the fridge compartment, in a part called the evaporator. This is where the real magic happens. The refrigerant, which is this super cold, low-pressure mix of liquid and vapor, starts flowing through these coils.
And check this out, this shows it perfectly. On the left, you've got the evaporator in the system. Now look at our perfect map on the right. As the refrigerant sucks up the heat from your food, it actually starts to boil and turns completely into a gas. That journey is that flat line from point 4 to point 1. It's absorbing energy, but the pressure stays nice and constant.
Okay, now, a refrigerant is a low-pressure gas, but it's loaded up with all that heat it just stole. We need a way to force it to let go of that heat. And that is the job of the compressor. It really is the heart of the whole system. It just grabs that gas and puts it under some serious pressure.
Let's hop back to our map and see what this looks like. You see the compressor on the left, and on our map on the right, bam, that's that huge vertical jump from point 1 to point 2. That's the compressor doing its work, cranking up both the pressure and the temperature like you wouldn't believe. It's now a superheated, high-pressure vapor. Now this super hot, high-pressure gas zips over to the condenser coils. The ones usually on the back of your fridge or underneath. And because it's now way hotter than your kitchen, the heat just naturally flows right out of the refrigerant and into the room. This is exactly why the back of your fridge feels warm to the touch.
Looking at our map again, this part of the journey is that top line, moving from point 2 to point 3. As our hero refrigerant dumps all that heat, it cools down and condenses back into a liquid, all while staying under that intense high pressure. Mission accomplished. Heat payload has been successfully delivered.
We're on the home stretch. This high-pressure liquid now makes its way to the expansion valve. Now, this thing is basically a tiny little nozzle that causes a massive, sudden drop in pressure. And thanks to physics, when you do that to a liquid, suddenly drop the pressure, its temperature just plummets.
And this is it, the final leg of our perfect trip. On the map, it's that straight drop from point 3 right back down to where we started, at point 4. Our hero is once again a super cold, low-pressure liquid ready to head back into the evaporator and absorb a whole new batch of heat. A perfect, neat rectangle.
And so our hero completes its perfect, frictionless, and endlessly efficient journey. Or does it? Because, as we all know, the real world is never ever that neat and tidy.
This is where theory gets a big old reality check. That perfect cycle is a great way to understand the basics, but it makes a whole bunch of assumptions that just are not true for the actual fridge sitting in your kitchen right now.
Yeah, that neat, perfect cycle we just walked through, it's a useful myth. The real journey our refrigerant hero takes is, well, it's a lot messier. And every single one of those messes, like friction and heat loss, is what makes your fridge work harder and use more electricity. So what's messing things up? Well, for starters, there's friction. As the refrigerant flows through the pipes, it loses a bit of pressure. The compressor isn't 100% efficient either. It generates extra heat and needs more energy to do its job. And finally, heat doesn't always stay put. It can leak into the cold pipes from the warm kitchen. And here's the really cool part. Engineers can actually map all these real-world problems. We can literally compare the perfect imaginary journey to the one that's actually happening inside your fridge.
Now, before we look at the map, here's a quick key. Don't worry, it's simple. The vertical axis, P, that's just pressure. The higher up you go, the more squeeze. The horizontal axis, I, is enthalpy, which is really just a fancy word for the total energy the refrigerant is carrying. The more you go to the right, the more energy it has.
And here we go, the moment of truth. On the left, our beautiful, perfect rectangle. And on the right, well, welcome to the real world. Look at that thing. It's all distorted, slanted, and bent out of shape. And every one of those imperfections tells a story of wasted energy.
Let's break it down. See how the top and bottom lines aren't flat anymore? They're sloping. That's the pressure being lost to friction. And look at that compression line, the one going from 1 up to 2 prime. See how it slants off to the right? That extra little bit of space to the right represents all the extra energy, the extra work the compressor had to do because of those real-world problems.
So who cares, right? It's just some squiggly lines on an engineering chart. Well, you care, or at least your wallet does. This difference between that perfect ideal and the messy reality, that hits your electricity bill every single month.
Let's look at some actual numbers from the source material. In this real-world example, to get 34 kilowatts of cooling power, that's the heat being pulled out of the cold space, the compressor had to use 14.3 kilowatts of electricity. That's the trade-off.
Now, if you divide the cooling you get out by the energy you put in, you get this number called the coefficient of performance, or COP. In this case, it's 2.38. Just think of this number as an efficiency score for your fridge. The higher the number, the better. It means you're getting more cooling for your buck. And every single one of those distortions on that real-world map is dragging that score down.
And really, that brings us to the final big idea here. That gap between the perfect rectangle and the messy real-world shape, it's not just wasted energy. It's a huge opportunity. It's the challenge for engineers to close that gap, to design better parts that fight back against friction and heat loss. So the next time you hear your fridge quietly humming away, remember the secret, imperfect journey happening inside. And just think, what if we could make that journey just a little more perfect?